In this next question, we have a rational function f of x, which is 2x plus 4 divided by 4 minus x squared. And we want to find all values of x in part A, where this function is discontinuous. Okay, so if I continue on with my function notation, a general strategy is that when you're dealing with a rational function, you want to try your best to factor the numerator and the denominator. On the numerator, I can factor out a 2, so I get x plus 2. And then on the denominator, I have a difference of squares. So all you're doing here is taking the square root of 4 and the square root of x squared. So I get 2 minus x and 2 plus x. Okay, from here on, I can see that there's an x plus 2 on the numerator and a 2 plus x on the denominator. So what that means is we have a whole at x equals to negative 2. All right, then we can just cancel those off. And if I take a look at this part right here, if I set that equal to 0, 2 minus x equals to 0, that means x would equal to positive 2, and that means we have a vertical asymptote at the other x value, which is positive 2, so x equals to 2. So those are your values of x, where your function is discontinuous for part A. Moving on to part B, we got to find the equations of the vertical and the horizontal asymptotes. All right, so if we just rewrite the original rational function again, I have 2x plus 4 divided by, and if I just kind of change the order of the denominator such that I have negative x squared plus 4, I can look at the powers here. There's a power of 1 on the numerator on that x variable, and on the denominator, the x variable has a power 2. So whenever the denominator has a higher power, then we can say that the horizontal asymptote by definition is always at the line y equals to 0, and that's because the power in the denominator is greater than the power in the numerator. Okay, and once again, doing the same steps from part A of this question, if we go ahead and factor here, so I believe that was 2 minus x and 2 plus x. If we go ahead and factor there, I mean, this is where you have the whole, and this tells you where this is where you have your vertical asymptote. So your vertical asymptote is at x equals to 2 there. Okay, so that's kind of repeating the same question from part A. So once again, for part B, the question was find the equations of the vertical asymptote, which is right there. And then we have to find the equations of the horizontal asymptote, which is right there. For the last part for this particular problem, the question states that we need to find the limit of f at each of the discontinuous points. So back from part A, we had the discontinuous points at x equals 2 and x equals to negative 2, and we want to find the limit at each of those x values. Okay, so let's go ahead and start off with the situation when x is equal to negative 2. That's where we have the whole. So we're going to write out a limit statement. So the limit as x approaches negative 2, and then let's go ahead and just factor out the numerator again. I have a 2 bracket x plus 2, and then the denominator was 2 plus x and 2 minus x. Okay, and once again, we've stated that we can cancel off those two factors right there. So we have the limit as x approaches negative 2, and what we're left with now is just 2 divided by 2 minus x. Now, if we just do a direct substitution here, if we take this negative 2 and plug it in for the denominator, what will happen next is we have 2 on the numerator, and then on the denominator we have 2 minus bracket negative 2. And that gives us a value of 2 over 4, which equals to 1/2. Okay, so what that really means is when x equals to negative 2, the y value that we approach is 1/2, and negative 2 comma 1/2 is the coordinates of the whole. Okay, so that is finding the limit of f at the first discontinuous point, which is when x equals to negative 2. Now let's take a look at how we can approach the vertical asymptote when x equals to positive 2. Okay, so just kind of erasing this and erasing that. Let me just kind of erase all this. Okay, when we're approaching 2, because we have a vertical asymptote, we have to approach both 2 from the right-hand side, and we also have to approach the vertical asymptote from the left-hand side. Okay, so let me just set up another function there. Okay, so when we're approaching the vertical asymptote, once again, we have to look at the vertical asymptote from both the left and right-hand sides of 2. And in order to execute this particular problem now, we need to use the horizontal line method here, where a 2 goes in the middle. And then we need a left side and a right side. Okay, so numbers on the left-hand side of 2 are numbers like 1.9, and numbers on the right-hand side of 2 are numbers like 2.01. Then from here on, we just do a direct substitution here. So we have 2 on the numerator there, and if we're taking numbers on the right-hand side of 2, we can use 2.01. So now I have 2 minus 2.01. And it turns out that the numerator is going to be positive, the denominator is going to be negative, so positive over negative is going to be negative infinity. Okay, so that's how the vertical asymptote is approaching when we approach 2 from the right-hand side. Now, if I take a look at the limit as x approaches 2 from the left-hand side, now we can use number 1.9, and we can do a direct substitution now. So I have 2 on the numerator divided by 2 minus 1.9. And clearly from here, the numerator is positive, the denominator is positive, so positive over positive will be positive infinity. Okay, so that means the overall limit does not exist. So if I just write the overall limit now, x approaches 2, since the left-hand and right-hand limits are not the same, the limit when x approaches 2 is actually, it doesn't exist. Okay, and maybe the final thing I'll do before I finish off this problem is I will just show you a little visual sketch of what's going on. So there it is for this particular problem here. When we're approaching 2 from the right-hand side, we are going to negative infinity. And if we're approaching 2 from the left-hand side, we're actually going to positive infinity. And there's my coordinates of my hole. And the horizontal asymptote here, I guess if I bring out a different color here, the horizontal asymptote is at y equals to 0 right here. And that's the basic sketch of this graph with some limit notation there showing you how the graph behaves when we approach 2 from the left and the right. We have a similar follow-up question where once again we're given a function f of x, which is this rational function right here. And for part 1 of this question, we need to find all values of x at which f is discontinuous. Okay, so if I take a look at this rational function, you may want to start by factoring the numerator, which is 2x plus 1 times x minus 1, and then let's go ahead and factor the denominator using a difference of squares. So this is the classic, just x plus 1 and x minus 1. Okay, so at this situation here, the x minus 1's cancel off, so that means we have a hole at x equals to positive 1. And over here, this means we have a vertical asymptote at x equals to negative 1. All right, so the values of x which were discontinuous are pretty much, if I combine both answers, x would equal to positive and negative 1. So those are the x values at which the function is discontinuous. Okay, let's move on to the next question here. And for the next question here, same function, and now we need to find the equations of the vertical and horizontal asymptote. Okay, from the previous question, we already found the vertical asymptote, right? So that was at, I believe that was at x equals to negative 1. Right, so you just kind of, let's just go ahead and just factor the numerator again. So this gave us 2x plus 1 and x minus 1, and then the denominator was x plus 1 and x minus 1, right? So once again, the vertical asymptote is right there. Okay, and then we're going to find the equations of the horizontal asymptote. Now the horizontal asymptote isn't too bad because we can do this by inspection. Okay, so since the power in the numerator is x squared and the power in the denominator is x squared, the powers are the same. We just take a look at the leading coefficients, the 2 and the 1. All right, so that means the horizontal asymptote is at the horizontal line of 2 over 1, and that means 2 over 1 is just y equals to 2. So there's the equation of the horizontal asymptote, and here is the equation of the vertical asymptote. And that's it for that particular question. Okay, for the next question, we need to find the limit of f at each of the discontinuous points. Okay, so we've already established that the vertical asymptote is at x equals to -1, and the whole will be at x equals to +1, right? Okay, so let's start working with the whole at x equals to -1. This isn't too bad. So first of all, we need to set up a limit statement. So the limit as x approaches 1, this is where the whole is at. And then if I go ahead and factor the, you know what, let's just factor the function up here again for the third time. And I apologize for just kind of repeating the same information again here. So, okay, so if I go ahead and cross those out, what really survives is really the 2x plus 1 all over the x plus 1. Okay, and then if we go ahead and just do a direct substitution for x equals to 1, we get a value of 2 times 1 plus 1 all over 1 plus 1, and that gives us a value of 3 over 2. Okay, so what that means is at the whole, the x value is 1 and the y value is 3 over 2, and that is the coordinates of the whole. Okay, so that's it when we take the limit as x approaches 1 for the whole. Now, now that we've finished that, let's take a look at the next case here. If I want to take a look at the vertical asymptote, this one takes a little bit more work. Whenever you have a vertical asymptote, you have to approach the value from the right-hand side, and you have to find the limit of that vertical asymptote when we approach it from the left-hand side. So a little bit of work to do when we're dealing with the vertical asymptote. And the method that we're going to use is the horizontal line method. So if I go ahead and just draw a horizontal line over here, the number in the middle is going to be -1. And then obviously we need a left-hand side and a right-hand side. So you want to be very careful when you're picking your numbers here so that you're picking the right numbers. A number on the right-hand side could be a -0.9. A number on the left-hand side could be -1.1. Okay, so if we're approaching this value of -1 from the right-hand side, let's just take this -0.9 and let's go ahead and just plug that in. So that's 2 times -0.9 plus 1 all over -0.9 plus 1. Okay, so if I evaluate those numbers there, let's go ahead and see if we can do this. I guess the numerator is going to be negative, and the denominator is also going to be, I guess that's going to be positive. So negative over positive is going to be negative infinity. So as we approach -1 from the right-hand side, we get a negative infinity there. Okay, let's go back to the next limit here. So let's take the number on the left-hand side now, which is -1.1. If we go and plug that in, we get 2 times -1.1 plus 1 all over -1.1 plus 1. Okay, if I evaluate this, 2 times -1.1 plus 1, that gives us a negative number, and on the denominator that's also negative, so this gives us positive infinity. Okay, so clearly the overall limit as x approaches -1 of f of x, this is going to be does not exist because the left hand and right hand limits are not the same. And if we just go to the visual diagram here, there it is. And as you can see, as we're approaching the limit from the right hand side, we go to negative infinity. And if we approach the limit from -1 from the left hand side, we go to positive infinity right there, right? So that's how the graphs are behaving. It's going straight down. And I don't have this on here, but the horizontal asymptote, is going to be roughly y equals to, the horizontal asymptote was 3 over 2, I believe, right? No, 2. Y equals to 2. Okay, so that's what the general graph of this function would look like. Okay, one last question for this homework video guide, and for this question we're given a piecewise function And the question wants us to use the three-part definition of continuity to prove that the function is continuous. The function is continuous at x equals to 2. Okay, so over here on the left, I have the three-part definition continuity. So here's the first part, the second part, and the third part. Now for the first part, we need to show that f of a exists. Okay, so what is the a value, right? A is actually the x value that we're approaching, right? So what we're trying to say here is a would equal to 2. Okay, so if I want to show that f of a exists, we have to look at our inequalities. Which one of these functions actually takes the value of 2? Is it the top function or is it the bottom one? Well, clearly it's the bottom function, right? The bottom function actually has the value of 2. So if I want to go ahead and show that f of a exists, I need to plug in f of 2 here, and then I take my my denominator, sorry, the function on the bottom, which is negative x squared plus 6, and then we just evaluate this. So this will be negative 4 plus 6, and negative 4 plus 6 gives you a value of 2. All right, so f of 2 equals to 2. So that is part 1 there. Okay, so if I just kind of erase all this, let me just kind of put the final result over here. This implies that f of 2 equals to 2, and f of a exists. Okay, it exists because the y value is positive 2. Okay, now if I move on to the second part of the definition, I need to show that the limit exists as x approaches a. So in order to show that, I pretty much need to set up two limit statements. So I need to set the limit as x approaches 2 from the right, and the limit as x approaches 2 from the left. Okay, if I'm approaching 2 from the right, I'm pretty much dealing with everything on the right hand side of 2, right? So I'm taking the bottom function again, so this is going to be negative x squared plus 6. And then if I have x is less than 2, this is on the left of 2, right? So that means that this function will be down here, 3 over x plus 1 plus 1. Okay, so how do I solve these two limit problems? We solve them by using direct substitution. So I take my 2 and plug that in. Well, we just did this calculation, so it'll be negative bracket 2 squared plus 6, which equals to 2. And then if I go ahead and take this 2 and plug it in, we get 3 over 2 plus 1 plus 1, and that gives me, I guess, 3 over 3 plus 1, and that gives me 1 plus 1, which is 2. Okay, so it turns out that the left-hand limit and the right-hand limit are equal. If the left-hand and right-hand limits are equal, then we just shown that the limit does exist when x approaches a. And since f of a, this was f of 2, equals to the limit as x approaches 2 of f of x, we just have shown that this value there is 2, and we know this limit here is 2. So we just shown that that f of 2 equals to the limit as x approaches 2 of f of x. Therefore, using the three-part definition continuity, this is definitely continuous at x equals to 2 there. Okay, and just to kind of finish up, here's my graph here. Here's my function, and clearly at this particular point right there, it is continuous when x equals to 2. The left-hand limit and the right-hand limit are both equal to a height of 2 there, right? So that pretty much confirms that this function is continuous.